Okay, section 2.4. One of the tools that we'll use from algebra to solve a lot of problems throughout the school year, throughout the geometry curriculum, is solving systems of equations. And so we are going to talk about the different methods of solving systems of equations right now. So take a look at this. This is a system of equations. There's two equations of lines there. And what we're doing here is we're going to graph the two lines on a Cartesian coordinate system right up here. So I will go ahead and do that. So I'm looking at the first equation here. I'm going to go ahead and put this into slope-intercept form. So y equals negative x plus 5. And then the second one here, I'm going to go ahead and put this into slope-intercept form, or solve for y, in other words. And so y is going to be equal to 3/2 x minus 10. And what I'm going to do is I'm going to take this and I'm going to graph this up here on this Cartesian coordinate system. And so the first one is going to be y equals negative x plus 5. So 1, 2, 3, 4, 5 is the y intercept. And it's going to have a slope of negative 1. So it's going like something like this. And I think I need to draw this a little further out. So it's going to look something like that. And the next one is going to have, it's going to go through negative 10, so it's negative 10 is down here, almost off the thing. Up 3 over 2, up 3 over 2, up 3 over 2. Go ahead and graph that. And hopefully you can see that the point of intersection is going to be at 6, negative 1. That is the solution to the system of to this particular system of equations. This 6, negative 1. That point right here represents the only point in common between both of those lines. So if I plug in 6, negative 1 into both of these equations, it will satisfy both equations. Now there's other ways of solving this that you should have learned last year. The first one is called substitution method. So substitution method basically works like this. You would solve this like for y up here and take that y and substitute it for the y in the other equation. So it becomes 3x minus 2 times the quantity. Make sure you substitute using a parentheses, equals 20. I'm going to distribute this negative 2 and do distributive property. So plus 2x minus 10 equals 20. So I get 5x equals 30. X is equal to positive 6. And then I can plug it back into either of the equations. Probably makes sense to plug it into the first one. And you get y is equal to negative 1, which is good because that's what we found graphically. When we graphed the two equations, we found that 6, negative 1 was the solution to the system, or it was the only point that was in common between the two. Linear combination is the other method that we are going to ask you to know, to remember from last year, otherwise known as elimination method. Elimination method. It's also known as linear combination, or I believe that one of the books calls it multiplication addition algorithm. But in any case, whatever it's called, this is the one where you basically line up all the x's, line up all the y's, and all the constants in standard form, which we talked about in the last section. And one thing I think I failed to mention in the last section is that generally all these need to be constants. Okay, these need to be integers in front of all the all the variables. But in any case, I'm going to go ahead and recognize that, okay, if I want to eliminate the x's, I'm going to need to multiply this entire top equation by -3. And so let's rewrite this as -3x minus 3y equals -15. And then I'm just going to rewrite the bottom equation down here. And now I can go ahead and add the two equations together. I'm allowed to do this because all the stuff on the left is equal to all the stuff on the right. All the stuff on the left is equal to all the stuff on the right. So if I add all the stuff on the left together, it should still equal all the stuff on the right. Okay, but the nice thing is when I add this stuff together here, I'm going to end up with -5y equals 5. So y is going to end up being equal to -1. The nice thing, if you notice there, is that we eliminated the x's, and we ended up just solving for y. The other thing you can do here is just plug it back in, plug in -1 back into the first equation and solve for x. Or what I could have done is on more complicated problems, I can go ahead and I can solve for, I can multiply the top equation by +2. So I can redo the elimination method again. So multiply the top equation by 2. So 2x plus 2y equals 10. Rewrite the bottom equation, 3x minus 2y equals 20. Add the two equations together. Hopefully you can see that we can eliminate the y's. So I get 5x equals 30, or x is equal to 6. And guess what? We ended up with exactly the same thing that we were doing in the two previous methods of solving systems. Okay, and then what we'll do is we'll apply that to some stuff that we just learned in the previous section. So I'm given a triangle. Let's try this problem here. Given a triangle with vertices at 3, +6, 1, 2, 3, 4, 5, 6. That's my A. My B is -3, +4, 1, 2, 3, 4. There's my B. My C is +4, -2, right here. There's my C. Connect the dots. Got a nice little triangle there. Find the intersection of the perpendicular bisector of AB and the altitude to BC. So what I need to do is I need to find the equation for this one and the equation for this guy. So let's go ahead and do that. Let's find the intersection of the perpendicular bisector. Let's find the perpendicular bisector of AB first. Perpendicular bisector is going to go through the midpoint and be perpendicular to AB. So the equation of that is going to be, let's see, the midpoint between A and B. I can just see that graphically is just going to be 0, 5. Is going to be the midpoint. And the slope I'm going to get from, well, I know the slope of AB, and it's just going to be perpendicular to that, so it's the opposite reciprocal of that. I can actually see the slope is going to be up 2 and over 6, so it's 2 divided by 6. Remember, it's a positive slope if it's rising from left to right, negative slope if it's going downward from left to right. So the slope's going to be 1/3, which means that the slope of the perpendicular line is going to be actually -3. And so if I look at this thing, that means that the perpendicular bisector, I know that this is actually the y-intercept, so I can put this into y equals mx plus b form. So y equals -3x plus 5. There's the equation of the perpendicular bisector. Now, let's go after the altitude drawn to BC. So we know that it's got to be, if it's drawn to BC, it's got to start at this vertex up here, and it's going to be drawn perpendicular to BC like this. I already have a point. The point is going to be A, so I'm going to write that down here, 3, 6. I can find the slope of BC, and that slope is going to be 6 over -7, which tells me that the perpendicular slope is going to be the opposite reciprocal of that, or 7 divided by 6. That means the equation is going to be, let's put this into point slope form, since I have a point and a slope, y minus 6 equals 7 over 6 times the quantity x minus 3. And that means that this, what I'm looking for is the intersection, if I'm solving the system here, the intersection between those. So solve that system. And then probably the easiest thing to do is just to do substitution. Take this, substitute it for y right there. And if I solve this thing, I'm just going to cheat here. And let's see, I ended up with, I think, x is equal to 3/5. Hopefully you're going to check my work on this. And y, if you solve the system, ends up being 16 over 5. You will get some ugly numbers like that. And, you know, in truth, most of real life are ugly numbers like that. So that's reality. All right, let's jump to the backside. I want to show you a couple things on the backside, and then I'm going to let you try some problems. So we're here on the backside of this worksheet, and what I wanted to do is, I'm not going to go through every single one of these, but I do want to talk about this. There's a couple of ways you can solve each of these. If you want to practice both ways, you can practice both ways. More importantly, I want to point out that sometimes there's a better way to solve these than the other. I can choose between substitution method or elimination method, linear combination. If I look at this first problem here, because I already have x and negative y there, probably the best method to use is just substitution, since I can just solve one of these for x. X is equal to y plus 9, and then just go ahead and do substitution. I could do elimination if I wanted to. Some people just prefer using elimination for everything. Some prefer using substitution for everything. But there is a better way to, you know, there's definitely ways that you can choose to do the better method. This is going to be 5 negative 4 when you go ahead and solve that for x and y. The next one here, what you're going to end up with when you solve this next one is you're going to end up with something like 0 equals 0 or 19 equals 19, something like that. And what that basically means is, hopefully you remember this from last year, that you actually have two equations here of the exact same line. And so when you're solving the system, all the intersections are basically the entire line itself. This next one here, if you look at this, probably the method that you want to do is elimination method. Now you can keep in mind that you can go ahead and you can multiply both equations. So for example, this one, I can multiply the top equation by -5, for example, and the bottom equation by +3. And so what I'm going to end up with when I do that is I'm going to end up with -15x plus 10y equals 20, and +15x plus 9y equals -3. And now I can, if you look at this, I can add the two equations together and the x's will drop out. When I do this, I'm going to get something not so great looking, like -14 over 19, comma 17 over 19. And like I said, on the front side, those are okay, especially when we're in this 4-level class environment. Some of those problems are going to be okay. Some of those are going to be okay. This next one here, when you solve this system, you're going to end up with something like 40 equals 17, which we know is not really true. So for this, there's going to be no solution. What does that mean? If you think about this graphically, what would have no solution as far as no intersections? And the only thing you would have here is you would end up with two lines that are parallel to each other. So these are parallel lines. And if I jump down to the bottom here, let's talk about this, because this does pop up every now and then, where you have to solve a system that looks something like this, and you're thinking, oh no, that looks terrible. But the nice thing is, if you look at this, if I just add the two equations together, the y squareds are going to drop out. The y's are going to drop out. So I get 2x squareds equals 32. Divide both sides by 2. X squared equals 16. X equals plus or minus 4. Okay, keeping in mind here that when I take the square root of both sides here, I actually get the absolute value of x equals 4, which leads me to x being equal to plus or minus 4. And when I plug it in, I'm going to plug in both x's and y's. I'm going to get two different values for the y's. So when I plug in positive 4, I'm going to get 3 and negative 3. And when I plug in negative 4, I'm going to get 3 and negative 3. So there's actually 4 solutions to this problem. 4, 3, 4, negative 3, negative 4, 3, negative 4, negative 3, like this. And those would be the intersections of that system here. And in case you're wondering, this is basically a circle. This is what we call a hyperbola, which you'll learn about in algebra to the class after this class you're currently taking, this geometry class. Okay? I'm going to stop here and let you go ahead and try some problems. All right. Take care.